I will introduce myself. My name is Nimish Desai, Indian number 1. Go ahead.
Kannesan Chandrasekhar, Indian number 2. I work in NSX engineering.
And I work in the NSX product marketing, technical solution engineer, whatever the title you want to give me. But this session is 60 minutes. It's a lot of stuff in it. We can't cover everything. Unfortunately, because of the way VMware format works, I don't like it. It's 60 minutes is not enough to describe such a large architecture. So we'll keep few things, but I will give you pointers to the design guide written by Indian and Italian. Okay, Max Ardika has good contributions. Shekhar has done a fantastic job of screening my PowerPoints, making sure there is a eventually consistent truth is told.
Just like our controllers.
Yes, exactly, like big data. We want to remain eventually consistent in truth, right? So ask any questions. My friend, you're bored. He's bored already. Maybe a wrong class. How many people are networking people? Okay. Most of the guys are like what? vSphere, VM, virtualization, storage. All right, good. So this class is heavily towards networking because it is all about networking, right? So ask any questions. I might defer you a little bit later. I might run 10 minutes late, and you can suffer 10 minutes of your time with me. So it's around 70 minutes, I will finish it, right? And Ganesh is going to jump in where necessary, or he will help you out, etc. But to reduce the discontinuity of conversation, he's generous that I talk, right?
Oh, yeah.
Which is a mistake after
Nimish does a fantastic job in communicating, so I'm going to let him talk, but I'll be sticking around for any questions afterwards or in the middle. And please feel free to come up front. Nimish looks scary, but he's a great guy.
You guys are sleepy actually, over there, I know. So let's get started. So to start with the disclaimer, I'm not a lawyer and I don't care about this slide. The session has 5 major topics. The major topic is around deployment, design consideration, SDDC, how it plays a role, etc. So I will spend most of the time in session or the topic number 3 as we progress. By the time you should have been all gone to this set of classes. How many people has attended NSX introduction? Fantastic news. That's a good news for the second session, right? So you have some idea about how things operate. So I don't talk about how things operate internally, right? Functional technology, I don't talk, but I do use technology to explain what design choices you need to make, right? So hopefully you have some background. And the SDDC, this is a marketing slide, but it has a good narrative. If you understand it, that we are not trying to here say there is a war between software and hardware. They are twin brothers. You can't avoid one without others, right? What is important in this narrative is the idea of what level of control, intelligence, automations that can be exploited with the use of software that was not previously possible. So use good hardware. However, the controls, world's largest companies are becoming software companies, as you know, Google, Facebook, Amazon, etc. And they all leverage software as their power, right? So the idea is in the mobile world, in the agility world, everything I want yesterday world, the software becomes your friend to leverage certain things that you could not do with this demarcation point that you have with the hardware and software from the networking viewpoint, right? So narrative is important, acceptance is important, right? So I will quote Gandhi, and I repeat this because I think I like that. When Britishers used to own us when I was Indian, the first thing was they ignore, then they laugh at you, then they fight, and then finally they accept, right? So we are in the fighting stage of war about ideas that where the architecturally things are going, and some are the pioneers are adapting it. I'm sure you will adapt more as we come next year. There will be a significant amount of adaptation of NSX, right? So it's real. Evolution of network virtualization principles, introduction of NSX, classical networking just doesn't cut it. It's a little bit hard line to argue. What it means is actually is that there are a lot of configurations, complexity has evolved over last 20 years to make network stable, make intelligence in the network, etc., right? So what we are saying is by doing that, you are coupling few fundamental underlying principles, logical configurations attached with your physical topology. So it's not that flexible to change the physical topology, but you try to make it better. A lot of good companies, a lot of good internet works on those sort of configurations, so it's not a denial of those technologies not important, but important thing is to avoid these type of a complex configurations and make the network as simple as you can. So network become actually a system backbone, a system bus, very simple transport network. That doesn't mean you're not gonna retire your network life overnight, right? It's not that, right? The internet, do you care when you watch YouTube, which hop it goes through and what configuration you do? It's the end user experience we are after, which is what? Agility, automations, just-in-time networking, that is important, right? So how does it solve those challenges? So we have to faithfully reproduce some of the basic component of networking, right? So it tries to articulate that this technology or NSX is topology agnostic. Layer 2, layer 3, doesn't matter any combinations. What it does is it is any vendor network you can use because the intelligence is abstracted in such a way that you can do your virtualization job without worrying about what's the underlying network is, but it needs to be stable. IP fabric, configure once so that you don't have to retouch it every time the VLAN change occurs or your virtualization's concept occurs or the workload behavior change. Flexibility and availability, of course, is important, as you can say, time to deploy, mobility, availability with the layer 2 and layer 3 networks. It has to be highly available because you have reached the level of network stability to the point where a largest transactions runs on those veins of those companies, right? Security is overused term in terms of like, hey, it's important, and everybody says, yep, agree. It's important. Yep, agree. And if you reach today's newspaper, 5 major banks got attacked. You heard that, right? Right. So that doesn't mean that I'm gonna solve world hunger in security, okay? Key is that develop a underlying security platform, and NSX provides that underlying security platform in such a way that you can use the other ecosystem partner to reach certain goals, compliance roles, the inoculation roles, redirection of traffic to the physical hardware. So we're not trying to conquer the physical hardware or physical firewall role because it has a value, because it looks into the application more deeply. But what we are providing is an infrastructure element in such a way that you can do NAT, firewall, load balancers, all those things in a software defined way or in a software construct so you can deploy it faster, easier. And finally, the Achilles heel, the single button phenomena. Everybody loves this single button business, like, right? Google car now has only 2 buttons, next generation, right? Start and emergency stop, right? Because humans meddles with the steering wheel too much, so they get rid of the steering wheel, right? That's all this automation is all about, right? Avoiding the human interaction. We don't want to become a CLI junkie to click junkie or vice versa. Ultimate goal is to consume these entities via API cloud consumption platform, right? That's where the power gets unleashed, right? So there are a bunch of components that requires to become a full portfolio of functionality you need in virtual world. I'm going to cover switching, routing, and firewalling. The rest of the other topics, there are very specific class. It's beyond the scope. There are other design recommendations exist on each individual components and how it all works together. But it's my apology because I can't do this in a given frame of time, right? So I ask whoever the executive you meet at VMworld, tell them that you need more than 60 minutes to discuss the new platform and technology, right? So architecture component, there is a session that goes deep about this. I will go through the introductions. You need a robust network, right? This is not a negotiable item, right? You need a robust network. On top, we run a data plane. What that means is you're forwarding packet in kernel. There are 3 distinct kernel modules that you need to worry about. Firewall kernel module, distributed routing kernel modules, and a logical switch, which is the virtual distributed switch, which is the underlying component that does a magic of VXLAN. Then there are 2 other components called Edge, NSX Edge. What Edge does, it provides you to interconnectivity and stateful services to the northbound network. So when you have a northbound, southbound traffic, that goes via that Edge virtual machine. There's one more virtual machine, it's called control VM, that is not depicted here, which allows you to interact distributed forwarding that occurs between inter-VM or inter-subnet within the host or across the host over the VXLAN, right? So those component makes it a data plane. That means all your packet guest traffic goes through these modules at the line rate, right? What else is there? You have to give an intelligence to this data plane. So when you learn about network, that gets stored or learned through a concept called controllers. Controller is the heart of the system who basically performs a lookup, ARP lookup, VTEP lookup, broadcast separation, etc. And it also allows you to create a network in which VXLAN does not require multicast. Controller has 3 different modes of operations, or the VXLAN has 3 different modes of operation. You can do it in a 3 different way, which in VXLAN standard requires you to run a multicast, but the controller gives a ability for you to run a VXLAN network in a unicast or a hybrid mode without having a heavy multicast requirement. The NSX manager is a component that you attach to your vCenter by giving its IP address. Then it installs that plugin, and that point onwards you manage most of the time the configurations and the defining logical network through vCenter. This relationship between NSX manager and vCenter is monogamous, right? 1-to-1 right now. What it does, it allows you to, it stores all the configurations, and that pushes the communications from NSX manager to the controller, as well as sometime NSX manager directly to the hypervisor, okay? In any of this case, the data packet doesn't go through this management or control plane. That are just to maintain the configurations, the learning of the network, how to forward a packet, etc., right? And finally, on top, there is a cloud consumption platform. How many people know VCAC? Okay, VCAC 6.0 has a very good integration, reasonable integration with NSX. 6.1 even brings even larger and deeper functionality where you can define a blueprint and deploy the blueprint as many times you require based on the criteria of load balancer, security tag, etc., right? So that's your API-driven platform. We have done a heavy lifting for you guys. Learn how to use this component, become a policy expert, right? The whole idea of cloud consumption is that how do you define a policy, how do you translate that into a codifiable template and then use it, right? So going back to the core of the subject, we will talk physical and logical interaction points, that how does the NSX interact with physical, how do you create the logical network. Then we'll go through the key points of NSX Edge design, logical routing, some of the topology, finish the conversation with microsegmentation, right? So let's get it started. First rule of Axiom or ED that I want to hamper is that NSX is agnostic to underlay topology, right? We don't have any war with it is layer 2 or layer 3 or any combination. Take a peek. Your existing network, greenfield design, we have some opinion on certain layer 2 or layer 3, etc. Only 2 requirements I'm asking from you guys. Number 1, it has to be IP fabric, right? No IPX, no SNA, etc., right? How many people know SNA? Yeah, sadly we are getting old. So MTU of 1600 is what I need, right? It's a VXLAN requirement. So your networks must support 1600 byte MTU on every single node, every single link that a VXLAN or the virtual domain of your network is. And we have a hidden slide that describes how to configure MTU for your network brethren, for the Arista as well as Cisco switches most of the time, right? I have excluded Dell or others because just lack of time, etc., to formalize the MTU consideration. So we'll talk briefly about few slides. I will go faster because this is a layer 2, layer 3 conversation. What is the difference in layer 2 versus layer 3? Layer 2 is everywhere there is a VLAN that propagates to every single rack, right? Or few rack. That's why we divide and conquer approach. We create a pod which creates your mobility zone, right? But the important part to remember from the NSX viewpoint is that there is a unique VLAN for a given storage vMotions or VXLAN or management, and there is a unique subnet association, right? And there is a default gateway in distribution, etc. The problem with this design is that it cannot scale because there is a constant war between a poor VM admin and a network guy who has learned it through experience not to stretch layer 2 because it's a finicky technology, it's a spanning tree based topology, right? Which does not work very well at the large scale. So the alternative is running a routing protocol all the way to the top of the rack. What does that mean? The routing protocols are robust. That's how your internet is working today, right? So this is an alternative that is in a growing trend because it's a scalable, it's stable, its troubleshooting techniques are very well known. Traceroute is important. Traceroute will tell you which hop you're going. There is a layer to traceroute, but it requires a rocket scientist to figure out the MAC addresses, right? That's the reason IPv6 is not lifting because it's too hard to remember the IPv6 address. 4 octet a human can remember, right? So you can trace, right? Traceroute. Of course, the die-hard network guy will say that there is a DNS, right? So how many people put DNS on every single interface of your routers? Almost none, right? Only on a backbone interface you put, right? So the idea is that the layer 3 is a lot more scalable, stable, working knowledge is important. It's important to understand that what that means. Typically, it's a spine leaf topology. That means multiple devices are forwarding simultaneously your user-based traffic. But the layer 2, layer 3 boundary, if you look at those over here, that exists on your top of the rack. When you do that, the northbound connectivity is all layer 3. Translation for you guys, in a traditional layer 3 network, each rack has a VLAN, each rack has a subnet, and each rack has a unique VLAN to subnet mapping. Another rack, another VLAN, another subnet. The twist in this conversation with the VXLAN, remember this, VLAN equal to subnet equal to rack in layer 3. VLAN equal to subnet equal to the entire pod or entire rack is equal to layer 2 topology. So it's important to understand that you still need a layer 2 connectivity from your host via 802.1q trunking VLANs. Why? Because you need a 4 basic kind of VLAN. VXLAN VLAN, management VLAN, vMotion VLAN, and a storage VLAN. You can have more, but the point is those get trunked all the way to the top of the rack, and that's where its significance ends, right? And we'll go through a little bit more on a layer 2, layer 3 topology, but before we try to organize the span of your VXLAN and how the layer 2, layer 3 works, you need some organizing principle around compute nodes or your compute workload, as well as your management center or clusters, and how does it interact with your edge design, which is the gateway to the northbound traffic, right? So some organizing principle that has value in it. The value is that you better not read the slide. I know. I put a lot of text in it so that you don't read the slide, but it's a reference. The key is the organizing critical component of it is that what is your vMotion boundary zone? What is your fault domain? what is your domain-specific understanding of compute workload versus a networking workload, which is the edge design. How do you decouple the VXLAN-based network to your network management, because you don't want to put your network management or the vCenter that manages the managers, say, goes into the same cluster, so that if the cluster blows, you are out of luck, right? So those are the principles, but the 3 key points I want you to remember. Number 1 is these physical, logical, and NSX. These are all work together, right? So impact of how the impact of a physical network is behaved layer 2 versus layer 3. How does the VXLAN works and how does VXLAN topology gets laid out? And finally, how do you do the vSphere cluster design along with NSX, right? So there are few sets of recommendations, same rack layout, compute, and edge and storage are combined rack, but then there are cluster overlay. So what we recommend is a horizontal cluster. Why? Because you reduce your failure domain for a given cluster to a single rack. If the single rack failure occurs, not all your compute low workload or virtual machine in a given cluster are all gone, right? So horizontal clustering. You can have a multiple cluster or vCenter running, depends upon your workload, but the key here is that as you grow or shrink, you add a rack or you add a set of hosts in the given set of clusters, and then you shrink or grow, depends upon a requirement of your workload for that design. The the edge and the management clusters in racks could be separate, completely separate. So you have a separate management rack, separate edge rack, or combined, right? You can use the logical resources. That will determine how large the network is, how much you want to manage the management within the compute zone, because management vCenter could be off-site, etc., right? So idea is, the point is here that you can stripe the cluster across, understand the edge clusters, management cluster, and compute cluster are 3 distinct entities, so that you can control the span of VXLAN, etc. That will make it clear. One important point, how do you do vCenter design with NSX, right? Simple versus flexible design. Because in a simple design, as I mentioned before, vCenter is related, or it's mapped to a single vCenter. That means you install this NSX manager and register to the vCenter here, IP address, VM get installed, IP is registered to that vCenter. The rule is that controller has to be registered to the same vCenter where you have registered your NSX manager to. So all are in the good, life is good here. Small design, or called simple design, single vCenter design. When you have a multiple vCenter, or why would I choose the flexible configurations with multiple vCenter? Typically, you have a management vCenter on which you have a multiple vCenter as a virtual machine. So you can create divide and conquer technology or topology, or the construct that NSX manager of domain A and domain B is installed in a management VC as a virtual machine, but it's registered to another VC that exists someplace as an IP address. So there is a relation from NSX manager to here. And what that means by rule, because NSX manager is registered to this vCenter, controller has to go into that domain. Okay? This way you can decouple. Sometime you want to upgrade your management vCenter for some other functionality. And let's say you keep your certain NSX domain with a certain vSphere release, etc. It decouples you from upgrade cycle, mobility management, span of control. Different VXLAN domain can be possible with the different compute load or business unit, etc. Right? So this is a flexible design, right? Confused, or everybody okay with this? So far, good? Everybody understand my English? Oh. Yes, we'll go one website. Correct, right. So that's why this vCenter 1 has a compute cluster, edge cluster as part of it, and this becomes your VXLAN domain. So you don't have to prepare this management VC for a VXLAN. Then it creates a circular dependency. We don't want that right now, right? So question. Back one slide. Here. Correct. So the question is, I think these, yeah, I will repeat. That's why I will repeat, absolutely. I didn't repeat his question, sorry. The question is, I think, let me, if I interpret that properly, that I described about this vCenter and different vCenter managing different management domain, etc. So the way I'm describing here vCenter 1 as a compute cluster zone, but that's, so he's saying that if you're showing the decoupling of vCenter, how come vCenter 1 is going RAID across it, right? Yes, technically this diagram is not exactly reflecting all the nuances that I talked about in the next slide.
Yeah, so basically I think this is sort of like a simplification of what he's talking about. So to answer your question exactly, you'd probably have another cluster here, which would probably be a management cluster, which is hosting only your management entities, like the management VC and things like that.
Actually, what he's saying is there is a separate vCenter for a management, right? And there is a vCenter that manages your compute load and edge cluster. So edge cluster and a compute cluster is in one vCenter. Management could be in another vCenter, and that was this whole purpose of this slide was. So it's not, you from Japan? Okay, sorry, I'm trying to identify because they're very meticulous about everything. So that's a good catch. Learning about VDS, VXLAN, transport zone, and logical networks, right? So this is another fundamental slide. Pay attention to this called green line. This green line is the fundamental to this entire VXLAN operations and why NSX make things more flexible for a virtual machine. That green line exists on two different domains. This is a domain A, which has a different subnet than domain B, which is this is essentially a top of the rack layer 3 design, in which subnet exists on a different zones, right? So idea is that this logical network runs across your top of the rack on a multiple compute zone or a compute host, and that gives a mobility for a virtual machine. So virtual machine 1 can talk to virtual machine 4 as if they are on the same wire. When they are on the same wire, it's layer 2 going over VXLAN domain. So VDS is an important concept. What makes that possible? Virtual distributed switch. Virtual distributed switch enables this VXLAN concept or zone, and that span of that VXLAN is the layer 2 communication zone. That's a green line. But then you will ask as a networking guy saying, how do I talk this layer 2 VM1 to VM4 without underlaying protocol? Because in a traditional routing, you requires a VLAN equal to subnet equal to rack. Remember I talked about it? To avoid or to overcome that, there is a concept called VXLAN transport network. It tunnels the informations from the virtual machine 1 via entity called virtual tunneling endpoint that connects to your VXLAN transport zone, right? So it uses this encapsulation technology at the hypervisor layer, ships the packet to the router or a switch, and the switch says, yeah, I know this is an IP packet. I'm going to just route it to the another VTEP, which could be another subnet or another same VLAN, doesn't matter. Point is that all I require is a one VLAN over here for a transport zone, and that's all I need. Can you spare me at least one VLAN? Yep. So it immunizes from these 4,000 VLAN restrictions. You can create as many segments and destroy it. You don't have to go and configure every single switch for this, right? That's the power of things, right? And there are design considerations around VTEP, virtual tunneling endpoint. If you notice it, I'm a little bit ahead of the game in terms of subnet is the same for layer 2 fabric. VTEP subnet differs per for layer 3 fabric. In other words, VTEP IP addresses are different from each TOR, right? So TOR 1, 2, you waving me? Hello? Yes, it's 30 minutes. That's why she's telling me to speed up. She wants to go home. This is a layer 2 topology, right? In this layer 2 topology, pay attention here. There is a VM kernel VLAN subnet scope. So when you define this VXLAN in a NSX, it creates a VM kernel. That VM kernel needs to go across all the racks because it's a layer 2 topology where VLAN goes everywhere. In this case, life is simple. There are only 4 unique VLAN, just an example. 4 utility VLAN, which are called VXLAN, transport management, vMotion, and storage. You can have more VLANs. But the idea, remember, is here the VLAN is unique and there is a unique subnet mapping. If you go back, next slide, this is a layer 3 top of the rack design. And if you look at it, I paid here attention to the VM kernel scope, VM kernel, same VLAN, unique subnet scope. What does that mean? That means is if you have a 5 rack, remember I talked about in a layer 3 top of the rack, there is a unique relationship between a subnet and a VLAN. Is unique on each rack. Here in a VXLAN topology, on a layer 3 topology, there is a slight twist of that rule. Here in a VXLAN, what we are saying is that for every rack, you keep a same VLAN. VLAN 10 for rack 1, rack 2, rack 3, rack n. Because VLAN has a local significance, so then you can duplicate those VLAN numbers. Why do you need that? Because I want that same one VLAN that I'm asking for you to configure for a VXLAN transport zone, right? Simplify the conversation, right? So when that happens, the subnet remains unique. So in other words, VLAN 10, unique subnet, closet 1. VLAN 10, unique subnet, closet 2. These VM kernel gets that IP address from those subnets via DHCP. Since VLAN is the same everywhere, you can DHCP it. VTEP will get an IP address from a DHCP server. There are some other intricacies involved called static routing is required because we offer a 2 different stack, standard stack, which where your storage, vMotion, etc. go, and there is called a enhanced high performance TCP/IP stack, which is where your VM kernel for your VXLAN traffic, control traffic goes, right? The data plane traffic always goes through VDS, as my friend corrected me the other day. The point here is that there are 2 different constructs. You have to be aware of what those differences are and take a design choices from onwards. So I have a bunch of hidden slides here, but we will move on. Is this a acceptable concept, or do you understand what I'm saying? A little fuzzy because it's true. Yeah, it is. It came a little bit, I'm a slow learner too, right? And it came a little late to me. It's like, oh, this is how it like, because we are so ingrained in thinking of old ways of doing a standard way, VLAN equal to subnet, or VLAN equal to subnet equal to closet idea, right? So I said, how can you have a same VLAN everywhere? Of course, in a layer 3 you can, because it loses its meaning at the top of the rack. But it has a huge importance. In a layer 2, it has to be unique, right? So we talk about a subnet design, the layer 2 versus layer 3, how do you map the VM kernel scope? Now the question is all about that you have this compute cluster, your management where your vCenter is registered, the NSX manager, controller, and you have a called edge cluster which talks to the northbound. You have a VTEPs, unique, this is a layer 3 top of the rack design, horizontally striped, 230, 240, different subnet, because it's a layer 3 top of the rack design. So how do you design VDS? So VDS design is very important. So one of the recommendations, without going into multiple permutation, is to have a standalone dedicated compute VDS and a edge VDS. And one would wonder saying, why do I need a 2 VDS? Because the compute VDS has a certain characteristic that we want to keep it local based on a compute workload design. Why? Because the uplink of the VDS defined across the entire VDS, right? So if you choose a LSCP, then LSCP is a standard configurations for your compute VDS. But you may not choose a LSCP for your edge cluster because it has a certain requirement of interacting with the northbound routing. So we'll make those concepts clear, but the idea and recommendation is to run a 2 separate VDS. So you will say, how in the world this talks across? If this compute VDS and this edge VDS, how does it talk? It talks over a common VXLAN transport zone. So VXLAN transport zone can have a multiple VDS, right? So we are localizing the compute function in a compute VDS, edge function into edge VDS, right? You can have a edge and management combined. There are nuances in it. There is an interesting Dell networking guide that we published that talks about it, what not to do in terms of if you are collapsing edge and management, what are the implications, etc. It's not super complicated, but it just gives you an idea that you can use the management function in the edge VDS, right? So what that also means, and I didn't talk a little bit more about this compute VDS and other reasons to understand the VDS design is twofold. Number one, this slide talks about 2 things. Number one, this cluster. Scale of NSX is bound by a vSphere scale, okay? That means how many virtual machine? Anybody has a wild guess how many virtual machine we support in vCenter?
5,000.
Pardon? Right, or marketing number 10,000. Right. So the idea is that a vSphere guy will kill me if they hear this, right? The idea is also the scope of mobility boundaries, right? So if you look at it, here is the cluster with VDS, another VDS, both is defined the DRS vMotion boundary. However, the connectivity boundary is across multiple VDS. This is why it's called transport zone boundary or VXLAN boundary. So you can communicate across multiple VDS on multiple virtual machine, but you cannot do DRS beyond your VDS boundary. So if you have a single VDS, this is a 2 large cluster with a single VDS spanning to a larger zone, where your boundary of manual vMotion across the cluster, this is, sorry, technically correct, its VDS is spanning across the cluster, you still have a certain limitations of the cluster to cluster DRS boundary. The manual vMotion boundary is now across VDS. Does it help?
Right. Basically, DRS is limited by cluster. DRS is limited to a cluster.
DRS is limited to cluster.
Whereas vMotion by itself spans the entire DVS.
Exactly. My alcohol came in the picture. So.
Oh, you're right.
Yeah. So VDS uplink design, what is that, right? It's ability to configure uplink is a critical design choice because it has a lots of different permutations you can do. Lot of requirements of convergence versus load balance versus simplified design. If you do LSCP, it requires elaborate configurations or some configuration with your network switches, etc. Right? So how do you choose? That will based on how you design your compute requirement and edge requirement, right? So if you look at the compatibility, the one thing that I want to make you aware is that NSX does not support load-based teaming. Every other method is available, okay? And the method you choose mostly depends upon what type of a workload, what type of a convergence you require, what type of a characteristic that you want to embed in your in each of these clusters. So typically we recommend a compute cluster in LSCP, typical server with the 210 gig link, both links are forwarding, a single VTEP. Why? Because configuration gets simplified. So when you run LSCP uplink, you can only configure one VTEP, virtual tunnel endpoint. You can configure multiple VTEP for certain reasons. I'm not going inside that, but the point being is that for most customer, most design, a single VTEP will do. That will drive your VXLAN traffic to 10 gig line rate. Okay? So idea here is that use compute cluster LSCP, explicit mode if the lag is not available, and an edge cluster, we prefer you use explicit failover. that avoids the need of a LSCP, and LSCP and Edge and routing protocol works mysteriously with certain vendors, right? And we'll go into that Edge cluster design with the multiple VTEPs or a single VTEP, but how do you interact with the northbound infrastructure that you have? So far, so good? Question? Repeat the question, please. Yeah, okay, let me repeat the question, and if you see it right. He's saying that why do we not support multiple VTEP on LACP? Am I asking the?
So I think, want to take it?
Go ahead.
Thanks. So basically the answer is there is no need to do that. So you, with LACP, you already have multiple physical NICs, right? That's actually spreading the load across, spreading the traffic load across. Now, you only need a single VTEP in this case because the underlying fabric actually helps to spread the load. Only in the case where LACP is not available do we recommend multiple VTEPs, in which case you will bind a VTEP to an uplink. And that will allow traffic from VMs to be spread across the two VTEPs to the two different PNICs.
Yeah, everybody heard this, what he's saying? Yeah, okay. I will enhance with one thing. It's called a LSCP. When you bound a channel, it's a single logical link. That means VTEP MAC address that we provide is single MAC address, right?
Correct.
That's the reason that you can not have a more than one VTEP over LSCP. So there's a exposure of MAC address that you need to talk to over the link, right? So if you have a two link, you can have a two VTEP. One VTEP goes on the left side, other VTEP on the right side. Both are represented by a MAC address because ultimately you're talking layer 2 domain. VXLAN is a layer 2 domain. You need to talk via MAC, right? That's why. Does it help? Yeah. Edge design. I'm a little bit running late, but I guess you guys are all interested in this, so we'll continue. NSX Edge design. What is NSX Edge? NSX Edge is a multi-function, multi-interface, multi-use virtual machine, right? So it can do routing, NAT, firewall, load balancer, etc. And it can deploy in a multiple form factors, small, compact, extra large, quad large, etc. Depends upon the performance and certain applications. It can do routing with the OSPF and BGP. It can also do the bandwidth consideration. Edge can run at the 10 gig level. It can run 20 gig, 30 gig, 40 gig, depends upon how you configure and spin up the virtual machine. Bottom line is you need three different characteristics that you need to consider. Edge placement of north-south traffic. We want that because Edge is used for all your virtual machines who wants to talk to whoever the users are there up north, right, in Canada. That's what it provides. It provides the interface and traffic forwarding to your northbound infrastructure. It has an implication with the cluster design and a bandwidth scaling, right? So if I'm not going into all the Edge design consideration because each is a heavy topic that we have to consider, etc. So when you deploy it, I'm trying to show you the idea of the design where the Edge, what consideration you need to do in terms of sizing, support, topology, OSPF, routing protocol, etc. So if you go, a first requirement we describe is called management and Edge cluster requirement. Remember we talked about it, why did we separate a compute load, compute clusters from the management or Edge cluster? These are the reasons. Number one reason is that typically management cluster requires layer 2 connectivity. So, and number two, Edge, when it talks to the northbound routing protocol, that also requires layer 2 connectivity. And if you deploy Edge into HA pair, that also requires layer 2 connectivity. What does that mean? That means if you design a network with two racks in mind, right? If you have two racks, you have to provide a layer 2 connectivity. There is no other way around it. So we want to confine that layer 2 to a pair of rack or a single rack, depends upon your design is, right? If you have a 4 top of the rack, you have to stretch across, or have a 2 top of the rack, you can cross, or you can do cross connect. So each rack has a single tower, right? And your host can cross connect to 2 different racks, so you can have a redundancy, but then you have to do the wiring mesh, etc. So there are different approaches to this design. How do you do the layer 2 design without having a too much risk impact on the conversation? So very specifically, we are talking now a edge rack design, all called edge cluster design. There are plethora of reasons. Number one, of course, reducing the stretching of a VLAN. So if you put edge VLAN in a compute cluster, right, all over the place, right, that means that VLAN that you have to stretch will go across multiple cluster or multiple network, right? And we don't want that in a layer 3 design or even in a layer 2 design, right? That because when a edge talks to your north or a switch via OSPF or BGP, it requires layer 2 connectivity. So we are confining this in the set of rack or set of dedicated cluster with a set of rack. It also allows you to localize route configuration. So when you know where your routing is from your virtual domain to the physical world, right? It also gives you a capability for a network folks, a dedicated a point for you to monitor the bandwidth, span of control, sending a separate syslog to the separate syslog server, because there is a separate operation and control. You can give a separate role in the vCenter so that only a network admin can spin up the virtual machine, the edge requirement, right? So there are lots of reasons to dedicate an edge with the cluster, as well as localizing the edge design within a couple of racks, right? There is another 2 factors. There are thing called cluster controllers that can also reside in the same edge rack, right? So there are more than one virtual machine that you will deploy in this cluster, and you have to size that cluster based on your requirement, the footprint of the edge, based on your services that you deploy, okay? This edge is critical for your bandwidth and the scaling and convergence viewpoint. So I'm going to talk about not all services, only routing services I will talk, right? In a routing services, that means you want to forward traffic from your southbound network to the northbound network. There are 3 ways you can configure edge. Number one is called edge HA pair. In edge HA pair, there is one active edge virtual machine who does forwarding, packet forwarding. It has a single routing adjacency. What does that mean? Routing adjacency defines that how I learn the network northbound and how do I advertise my network to the northbound, right? That is learned via a relationship between a physical router and edge over OSPF or EIGRP. That's a Freudian slip. OSPF or BGP. But what that also means is your throughput is limited via 10 gig. For a given compute workload, you can have only one edge HA pair, right? What that means is for a given cluster, you cannot send more than a 10 gig. That may be okay for most of the workload based on your requirement, right? But the convergence is little limited, it's a little longer, because the other key point that I missed here is that when a edge HA pair works, it synchronizes all the stateful services. So it synchronizes your forwarding information base called FIB table, NAT entries, load bearer virtual IPs, VPN tunnels, etc., right? So it's a stateful switchover. So one edge fails, this guy takes over. It has to restart all the services. It has to restart the OSPF or BGP peering relationship. But since the FIB table is synced, it continues forwarding a packet. There is some limitations. It has a little bit higher convergence. So if you do not like the convergence, or the convergence is longer for you guys, and you do not need a stateful services like NAT, load balancers in those edge virtual machine, then you can go with another model called standalone edge model, where you have one virtual machine active, other virtual machine is also active. However, you can only forward from only one virtual machine. But advantage of this design is that you have a peering relationship formed already. So when the one guy goes away, I can immediately start working on the other guy, so convergence is reduced. 3 to 4 second convergence here, right? Finally, again, both of this design has a limitation of 10 gig in an existing software release. In 3 weeks, maybe 4, maybe 5, I don't know exact number, we will release a NSX 6.1 release, which will allow you to configure more than one edge, actively forwarding. 10 minutes, keep coming 10 minutes, right? We are not leaving until we finish. So, this ECMP allows you to scale your bandwidth beyond 10 gig because it forms a equal cost path or called multiple path to your physical router. So you have if you do show IP route 10.10.10, it will give you 8 routes. That means 8 paths because it's going through via 8 virtual machines to forward your traffic. It will select one path for one session, depends upon how you configure the load hashing on a layer 3 routing, etc. But it is an incremental advantage. You need a 10 gig, deploy one edge. You need 20 gig, deploy another edge. You need 30, etc. up to 80 gig for a given routing domain. Then if you have another routing domain, you can deploy another 80 gig worth of bandwidth. So it's a linearly scalable architecture, horizontally scales. Currently, as we speak in a 6.1, we don't support stateful services, right? That does not mean that we cannot do a stateful services for certain workload. So you can have a workload that requires high bandwidth but not require those stateful services. Certain workload you require, you spin up the edge for them that can do a HA pair, right? HHA. So
edge designs concurrently.
Correct. Multiple edge design concurrently, and also this edge does not always has to reside on an edge cluster. Now I have twisted your brain. Why? Remember, I keep saying that it has to reside in an edge cluster. If you use a load balancer feature, then you can create an edge inside your logical segment near web, app, or DB tier. But then you are using only a load balancer functionality. That's why I say it's harder concept to absorb because we have put so much functionality in. It's a multi-use, multi-purpose, multiple places it can be utilized, right? Right.
So Nimish,
Yeah.
You talked about scale out for north to south. How about south to north?
Yeah, so I missed, that's a good point that what this conversation is about is a bidirectional ECMP. In other words, from north to the south, you have a 8 path, but from your virtual network, you also have a 8 path. I will make that clear in the next slide. That is, we are talking a logical routing topologies. What does that mean? Remember that green line that I described? That virtual machine exists on that green line across multiple racks. You can have hundreds of those, right? Right? You can have that green line represent one virtual network identifier in a VXLAN terminology called 5001. You can have a 5002, 5003, etc. And each those green, blue, yellow segment represents individual subnet. Now with virtual machine, if you have a 3-tier application, you have a 3 unique subnet for web, app, and DB. That means you have to route between them. How do you route? Natural inclination is you route via edge because edge is a router, right? You have right? However, that means every single traffic is going to the edge and coming back. So what we have done is a improvement, a significant improvement in a local forwarding. So we have introduced a concept called logical distributed router that has a control VM that forms a control plane adjacency or control plane communication with your edge. Remember the edge conversation? Edge forms the communications to northbound, but now with this control VM, edge also forms the adjacency with your southbound logical distributed router. That logical distributed router is nothing but a giant router with 1,000 interfaces. You can have up to 1,000 leaf, 1,000 green segment, of course with unique subnet, right? When you do that, and all of that interface that I do, logical interface you define, those logical interface becomes your default gateway. And guess what? Tricky part is it's 10.10.1 for every single host because that logical interface exists on all your hosts. Now, do you see the magic what's happening? That virtual machine moves, default gateway remains the same, right? If virtual machine green line talks to subnet, talks to the yellow line, what does it do? It sends a traffic to leaf 1. The router is sitting in every single host. It says, I know this route, it's directly connected, I'm going to forward the packet there. Localized forwarding, no hairpinning. So within the host, the traffic is always locally forwarded. You're going to say, what about the virtual machine? That green line existed in different hosts. So you have a host here, and if you have a virtual machine in single host, and it wants to talk to different virtual machine on a different host, we have a VXLAN. But then you're going to say, but no, the subnet, he wants to talk to subnet 1 to subnet 2. So we always forward traffic locally. In other words, we first do the routing, and the logical interface figures out, hey, this virtual machine does not belong to my local host. That means I have to bridge over the VXLAN to the other host via virtual tunnel endpoint by encapsulating the traffic, right? These deep design conversation is described or been told or taught by Max Hardika on a detailed conversation about routing configuration design. We'll talk, so go listen to his talk if it is recorded. I hope it is recorded. So we talked about logical distributed routing. You have to somehow plug that with the edge, right? That's what I'm talking about here. That's what Shekhar was talking about, that this distributed logical router that exists across your multiple hosts with multiple interfaces represented by web, app, and DB, this DLR forms a routing adjacency with your edge. In this model, it's forming a single adjacency because in edge HA pair model, you have a one path to go out, right? And the failover, etc., we talked about, that takes over and life is good. If you do the standalone model, then you have a two routing adjacency, but still one path out because it's not ECMP based in current release. If you deploy this topology for a higher convergence and later upgrade to 6.1, you get two routers, two adjacency, two path from your host because it has a multiple path available via routing peer adjacency, right? In this Mongo design, final state design, which is a classical conversation about multiple edges. So you have 8 edges that has a 8-way relationship all the way to the northbound. I have a 4 router. Why? Because in this design, I'm talking about multiple racks. Each rack has a pair of Tor. That means you're interacting 8 edges on a varieties of ways. If you look at it, there is a 2 lines, right? Blue and green that designate VLAN 10, VLAN 11, and that can repeat VLAN 10 and 11 as many times you want. It doesn't have to be a same. If you draw the line across the 4 routers, then it has to be unique, a single VLAN, right? You got the point? But important point is that this DLR, distributed logical router, via control VM forms an adjacency with all 8 edges. And then it programs that path into the host. And host says, hey, I have an 8-way to get out. So it will choose one of these edges to go out. Then edge will say, I have a 2 path to go out, VLAN 10, VLAN 11, the blue line and red line. And then it can distribute the load sharing across. So north to south, you have a 8 path. South to north, you have a 8 path. 8 path means you have a 80 gig bandwidth. North to south or south to north, right? So far so clear? She's feeling cold. Is it too cold? I don't like cold either.
Quick question before we move on. One, the DLR is a kernel module, correct? Kernel level?
Right.
So his question is the DLR a kernel module? Yes.
Yes.
Remember the original Sorry, go ahead.
I can answer it in more detail. So a DLR has got two components. One is a forwarding data path component, which is a kernel module. So it exists on every hypervisor. So it's sort of like directly attached to the VM in some sense. Then there is a control VM part of it, which Nimish talked about. That acts like a route server. That's a VM actually, but that exists out somewhere, and that talks to the edge and exchanges routes. So the control VM, when it learns a route from its next hop, which in this diagram is an edge, it will actually push that learned routes down to the data path modules, which is actually in the kernel via the controller.
Control plane, data plane.
Exactly. Exactly.
Second question, can you deploy the edge appliances with no routing at all, just with the stateful services, the load balancing, the other services completely separate of the routing?
So the question is, can you deploy an edge appliance without routing with just a load balancing? I think Nimish talked about that earlier. You can have it as you can have it as a one-arm load balancer, for example.
You can have a one-arm load balancer that will do the job, right?
Taking lots of notes, Mr.
Oh, no. Keep them coming. It's good.
You're allowed to have more than one question because they're sitting right next to me here. This green t-shirt and black t-shirt guys are still awake. That's scary. That's good. NSX topology. NSX topology, we talk about how do you implement this design in a variety of format, right? Am I on a speaker? Okay. Yeah. So let's talk the first design. It's called typical enterprise design. You have a DLR. You have a bunch of logical segment that is connected. Did you see that? This distributed routing across multiple hosts, multiple web app and DB tiers. They are all connected to a single NSX Edge HA pair, right? The HA pair I'm not showing, but it forms the adjacency over the VXLAN transit link. Then NSX Edge pairs with your physical router. Simplest topology, what it does is that you deploy these NSX and DLR at once. Now, you have just pre-provisioned your network, just configured once. You deployed your edge, so you can talk north-south. You deployed your distributed logical routers, one instance. Now you can deploy as many logical segments as you can on the southbound. So it gives you a flexibility of deploying multiple logical segments. It's a two-tier topology, localized forwarding in the distributed logical routing, north to south forwarding via NSX Edge, right? If you enhance this design, as we were talking, this edge can be replaced or can spin up multiple edges. That means you have a 80 gig routing, right? So this simple design can, with a 6.1, so there are two ways to scale edge performance or edge forwarding packet, right? The bandwidth. Edge scaling two ways, per tenant scaling. So for a given workload or a tenant, gets edge and a DLR. So you have a DLR means distributed logical router instance 1 and edge instance 1. They both get together. For another tenant, you have a LDR and an edge, third tenant, etc. You can scale per tenant per workload if you designate that way. Or you can say ECMP based scaling for a given distributed logical router, you can have up to 80 gig, right? So how do you do one more iteration of the design? Edge also allows you to configure more than one interfaces. So you can configure up to 9 interfaces. That means you can configure 9 different distinct logical routing instances. Why this is important? If you want to do multi-tenant design. Okay? If you have a multi-tenant design, you can connect that way. But keep in mind, the throughput is limited via one HA pair. Now you can deploy multiple edge HA pair. I'm not expanding these graphics further, but then that means the DLR, each logical router can have a multiple interfaces because it's a multi-interface edge design. What this design does not solve is if you require a true isolation, then you need to go to the last iteration of design called high-scale multi-tenant design, in which you have a 2 tiers of edge routing. This edge is called a provider edge, where it configures once, but each tenant comes on board, or each business unit come on board, or each workload comes on board. You can deploy this. But the advantage of this design is that it allows you to do netting. because you can do overlapping IP addresses. This tenant and that tenant can have a same subnet, but it gets translated over here to the unique IP on these two edges. Umair, we are okay with that, right? Yeah. And then this guy does the routing, right? So there are there are variety of combination. I know customers are imaginative and they will do something and will come and tell you, no, it's not supported. There are some certain unsupported topology. I'm not sharing that with you. I think we have in design guide, we talk about only these 3 topology. As we improve the design guide, we will tell you what not to do with this flexible things now you have. Don't wing it in any different directions, right? Still structured, policy, topology, architecture matters. He's asking, let me repeat the question and you answer, probably you can answer that. Maybe I did not hear. Did you hear the question?
We'll ask him to repeat, yeah. Can you repeat the question?
So if tenant needs more than 10 gig, right? You can deploy additional edge without that support, right?
Yes. So the question is, can the tenant NSX Edge Gateways also be scaled up for additional throughput? The answer is yes. Every one of these edges can actually be scaled up for.
Yeah, exactly. So it's an expandable entity. Each of these can expand to multiple. Each of these can expand multiple, and each of these has a. So yeah, that's why I'm saying you can go crazy with this spinning a virtual machines and have that, but have that thinking in the brain, right? That's why it's high scale multi-tenant topology, right? The last one, micro-segmentation, it's actually not doing a good treatment as much as I want. There's a detailed design guide. But the idea here is that a virtual world, inter-tenant, inter-virtual machine, intra-host, how do you protect it? 2 ways to do it. You have a physical firewall, which we are not replacing. It's a good idea to have it. And if you have a Palo Alto network, we can redirect the traffic over there. Edge firewall, again, Edge Fire in the 6.1 release onward, you can disable the Edge firewall. Okay. In the 6.0, there are cases you can disable it, but talk to us. But the point is that you can run an Edge firewall called perimeter firewall, and the distributed firewall is a distributed routing module kernel, which allows you to run a firewall at the VNIC level. And characteristic of that firewall is a stateful, it's vMotionable, it's RESTful programmable. It has a multitude of objects, data center, vCenter, logical switch, logical network, VXLAN, IP protocol, or different tool set that will comprises of thing called security groups. So you can assign a security groups to set of tenants or set of workload, okay? And when you do that, the flexibility of configuration and management goes away, right? Because as soon as you destroy that segment, that rules gets deprogrammed. As soon as you move that virtual machine, the set of rules that is on host 1 goes away, it gets reinstalled on a host 2. And it also have a stateful connections because the state is synchronized, right? You manage the state, right? So powerful example, security group. That's the reason we are promoting. The idea here is that fundamentally the efficiency that it brings in protecting, we are not saying that this is the best security things you can ever do, but it leverages you from doing a lot of things that is now possible with the security group and tags with Rapid7, all our ecosystem partners, Symantec, etc., right? So you can inoculate virtual machine, put it in a separate logical segment, Symantec comes in, affirms the patch, so you can develop a life cycle of VM. As soon as VM get deploys, he gets 0 access. Then you open the hole for your patching, 0 access. Then you open the hole for your application deployment, 0 access. Then you give it to operation saying deploy. That's where the operation guy deploys all the ports. So the fundamental idea is it's a zero trust security model. And there are 3 designs that's available. Number 1, where you group, it's called microsegmentation design, the one that we are promoting because it allows you to create a domain-specific expertise within the application tier or a workgroup-specific, workload-specific expertise. So here, what I'm doing is I'm consolidating a web tier traffic, all the web traffic in a single logical segment, and you assign saying web team, you figure out the security because you know all the open port, you know the workflow, you know the user access, etc. if you have a homogeneous web team. So these are all some of the organizational challenges, or you have to figure out what works, what doesn't work. And they have to talk to each other, so then you have to specifically open the hole from one virtual app to another app, and you have to manage intra-web virtual machine security and the inter-tier from web to app on individual basis. So that's seriously complex unless you design the policy and the framework, which is what defined by a security group. You export them into VCAC, and life is always better. In this topology, this concept is called application as a container model, in which web tier, application tier, and DB tier are all collapsed into single logical green line. That means the entire application guy can manage the behavior of that logical segment and says, who do we need to talk? Because I probably don't need to talk from web to the DB, so you can put a simple filter there. Rest of the things you can open because you know that is your domain. You can create a specific policy how this virtual machine operates. So it's not just about security, also vMotion, dynamic DRS, the CPU, etc. characteristic, right? And finally, there is a called DMZ design. In DMZ design, the idea is that you have a multiple segment connected to the single edge, or by the way, you can connect this logical segment to the edge. We are not recommending that because there are some other traffic redirection occurs. So we always prefer these app tiers and DB tiers, all the application segments resides on a distributed logical router, right? I don't talk about the topology that has a web tier directly connected to edge. If you look at the all HOL lab, that has a pretty simple configuration to illustrate the concept, where we are collapsing management and edge into a single cluster. We are connecting web to the edge interface, etc. Right? So there is other possibility, but the idea here is that you have a multi-interface design, and each has its security zone or domain, and within the security zone, you can protect the virtual machines through the policy management. Right? Finally, the nirvana, the VCAC. Lot of text. What we trying to say here, and I try to say is here, that we have created a basic 4 profile in a VCAC. So as soon as you turn off VCAC and send discovery mode, it discover NSX as an endpoint where it can program things. We can use 4 distinct profiles: routed, NAT, private, and external. Those profiles, when you turn up the virtual machine through API, gets attached. So if you need a routed virtual machine, so your IP addresses are all legal and legit, routable address to the internet or your intranet, then you can use routed profile. You need a NAT profile, then you can use a NAT profile. There are some dependencies. I implore you, there is a gentleman called Ray Budavari. By the way, there is a significant contribution to this design as well, more than I want to admit. But the idea is that the NATing, private profile, external profile, all those things can be exported and deployed along with the security group. So when you deploy it, the security group automatically get deployed from the VCAC as a template form called blueprint, right? So the automations is the next step that you should explore with the Ray's session that has been recorded probably with all the conversation about 6.0 and 6.1 release of VCAC. And by the way, it's not just VCAC, right? If you are gung-ho about your own API router or API interface and you want to create your own GUI, etc., knock yourself out, because these are all RESTful API conversation or calls, right? In fact, we provide more flexibility in API than a clicking or CLI-based configuration. So CLI-based read-only CLI mode. Reference design. So We have just updated our reference design 1.8 or whatever you want to call it. It's available on community vmware.com. It's important that you provide us a feedback. You don't like certain pictures, you don't like, there's no Kim Kardashian in it, okay? So don't expect everything from the doc. Plus, provide the feedback. This entire design is discussed there and a little bit more. There is another design called EMC SRM based design, multi-site with the source SRM backed multiple vPlex cluster, etc. That's there. Finally, we have a Dale reference architecture. It is primarily designed to have you applicable for a small and medium design with the Dale cluster advantage of converged network as well as a NSX on top of it, right? That reference architecture, Dale, that gentleman is over here. He has actually deployed in his lab and gone through all the certification or learning, etc. So he can help you. How do you build a Dale-based design? There are other design, but I'm not sharing with you right now. The key is that NSX is here. It's in production. It works with any topology, with scale, with automation, with security, and with ecosystem partner, right? There are long history will be created with this platform. There is no turning back. Learn from HOL lab. I have my email. We can talk offline. Talk to your VMware SE about deploying the POC. Learn and use this design, right? Thank you.